So we know we have about 23 people online. Maybe we can start.
Okay.
Yeah, I also think that we can start.
Oh, sorry. Is Sebastian also co-hosting too? What?
Yes.
Yeah, sometimes it's
Oh,
happened.
okay. Hey, Sebastian.
Uh,
Okay. I guess we can get started. Um, okay. Give me a second. Sorry. Okay, great. Yes. Hi, everyone. Welcome back to another session of the quantum computing meetup on Halloween. Well, I guess for Halloween weekend. Thanks for joining. We have Daniel Claudino once again. I think Daniel, you spoke like 1 year, last year, 2 years ago.
I think it was last year.
It was last year, yeah. So good to see you again. Um, and today he'll be talking about recent developments that alleviate some of the drawbacks that plague quantum simulation of chemistry in NISQ devices, specifically accuracy and accuracy that can be significantly improved by invoking similar arguments to those that elevated coupled cluster theory to be referred to as the gold standard of quantum chemistry. We show how many body perturbation theory can help improve the energetics of a number of molecules with no further burden to the quantum computer. Quick bio on Daniel. He finished his PhD at the University of Florida, and now he's currently working as a research scientist at Oak Ridge National Laboratory in Tennessee. So, yeah, I think you were there last year as well. So it's been a couple of years now. And without further ado, Daniel Claudino.
Well, thank you for the introduction, and thanks, Helen, again for inviting me. Yeah, I had a great time last time, so I hope we keep the tone here. So yeah, this time I'm going to talk about something that's fairly different that I honestly, I mean, a lot of this is actually was driven by a student of mine that I'm going to acknowledge uh, later in the presentation. And so yeah, this is stuff that we came up with and have been working on the past year or so. And this is the first time that I actually put together a talk for this, so I'm really excited about sharing this results with this audience. So this is a kind of quick like breakdown of the presentation. So I'm going to talk about two kind of directions that we took with this idea of kind of a reviving or incorporating perturbation theory within your typical kind of variational quantum eigensolver approach to solving chemistry on quantum computers. And that's kind of sandwiched between one introduction and a conclusion. So as for an introduction, for those who are not familiar or would question or have no idea why we would kind of connect chemistry with quantum computing. So this came out 2017 in one of the like most widespread kind of scientific communication, at least in the chemistry in chemical engineering space, saying, well, chemistry is the quantum computing's killer app. And I blame this article for a lot of the hype that came from thinking, well, quantum computing is going to solve all the chemistry world's problems at least. But there's some truth to that. So, and then later, this is a couple of years down the road, I think late 2019 or 2020, I think, that it came this report out of McKinsey that they were looking at kind of like of a market research perspective on what fields and what impact quantum computing could have on those fields and the timeline and things like that. So out of this, I highlight this area here, chemicals, obviously, but also pharmaceuticals are very closely connected to chemistry. And you can see they are all highlighted as, high impact fields. And we are talking about, over $500 billion value by 2035. So obviously this is all projected and doesn't necessarily mean it's going to materialize in that way, but I think it signals that the importance of chemistry for developing and maturing quantum computing as something that is going to be essential and recurring in computational workflows, even for industry applications. Now, after all this, I mean, we hear all these things, I mean, about all the potential of quantum computing and what you could do in revolutionizing materials and chemistry and pharmaceuticals. So yeah, this is what we have been sold, but then, you know, this is how it started and this is how it's going. I would say that we are at the kind of stone age of quantum computing still. But I don't mean that to discourage anybody, but actually to say, well, there's like so many things to do, and you know, we need a lot of hands to actually, you know, make all the promises that quantum computing can deliver real and materialize. Now, being a little more technical now, I found this quite funny, and I would say I'm bringing this up. You're gonna understand this in a second. So, I mean, everybody knows how to count up to 1 million, but it would take a lot of time. So it took this guy 89 days. You know, it was counting 16 hours a day. And it's all on YouTube if anyone wants to check out. So what I'm saying is, like, there are things that are simple, but the difficulty is not in the execution, is like then the amount of resources that it would take one to be able to do that, meaning, you know, time or space or energy, things of that sort. And how does that connect to our topic at hand here? So a lot of chemistry, or a lot of relevant chemistry, can be done by finding the low-lying energy eigenspectrum of the molecular Hamiltonian. And it's, you know, a relatively simple task. It's just, you know, it boils down to a matrix diagonalization. Now, if we have a basis of, if we try to resolve the spatial wave function, or in a spatial basis, because the angular part we kind of got figured out, and distribute the electrons in the system over those basis functions, you're going to see that we need this amount of space, or something that scales like that, to store all this information. This one here, which scales factorially. So if we think about a simple molecule like benzene, for example, you know, 6 carbon atoms, 6 hydrogen atoms, this would not, a simple calculation like this would not even fit like the best quantum computers that we have now. And they, in this paper here that I cite, they show where you can only treat this molecule with approximate methods, even on supercomputers. So we know how to solve the problem. We just don't have, you know, the computational power to do it. Now, obviously, we are trying to shoehorn this a quantum solution inside the you know, a classical compute machine, and then, well, Feynman is notorious for having reason about this back in the 80s, and then his basic idea is, well, if you have something that grows exponentially, so as you increase the size, or the you know, number of time steps, or something that accounts for, say, the dimensionality of the problem, and then you see that the amount of computation that you need to do increase, not in a like linear or lower polynomial fashion, but most of the time is actually exponentially. So then you're out of luck. So why don't we come up with a computer that the computer itself, its computational power scales on par with the problem at hand? So that's one of the reasons why we think, well, simulating quantum entities or systems is the prime candidate for quantum computers. Okay, so I think we take that idea, build a quantum computer, and then use it to simulate nature. Sounds quite simple, but obviously it's not. I mean, there are like lots of very smart people who have and are still working really hard on it, and we have all sorts of challenges and difficulties because, well, the computer is not isolated from the rest of the universe, so it has some level of interaction, which we just coined this umbrella term noise. So anything that it comes from the outside or anything that scrambles or affects your information in a way that's not the intended effect. So we impart or we act on where we can affect some change in the information that's carried by a quantum state through what we call gate. Don't worry about what it is. It's just the idea is like a mechanism through which we can impart those changes, and those obviously take some amount of time to be carried out. And as you need more and more gates, it takes more and more time. That it makes your computer more and more vulnerable to this effect that comes from the outside, and then the amount of time that the computer can endure this effect and still be able to deliver some trustworthy information is what we call coherence time. This is a very kind of introductory slide here, is just to give some context. You have a qubit is kind of the building block of quantum information, and you have states that live on the surface of this block sphere. So a gate is...
Excuse me, Daniel.
Yes.
Can I have one question for you?
Yes. Yeah, sure.
Could you say something about this chemistry and chemical structure? What kinds of things we want predict at this, and what it is more quantum than classical on the chemistry level? Because at present we can produce something on chemistry by doing a quantum computing on quantum machine on quantum quantum theory level. Yes, in traditional way.
Yeah, no, you can do it. Yeah, let me start by saying yes. What the types of applications that we see needing this a quantum computer for? So you have even ground states that are hard to define. It's not very typical in molecules that molecules ground states tend to be oftentimes fairly reasonable to understand. But a lot of important chemistry comes from excited states, for example. That's one case. And then there are excited states that are very hard to detail. And because of if you want to have a proper many-body theory to deal with those states, you start talking about methods that don't scale very well. So they become really costly very quickly, and then you can only apply them to very small molecules that oftentimes don't have any practical application in industry.
Okay, but I understand that you're talking about one molecule and its energy levels, yes? Can we use quantum computer for something that we can connect many molecules, the same molecules, and find what will happen, or how we can connect different kinds of molecules? It is okay for quantum computing, or it's too much?
Okay, could you rephrase your question? I'm not sure I understand.
Because as I understand, you told that we can use quantum computing and quantum computers for describing the energy level of molecules. Yes.
Yes.
Can
Sure.
we do something more that we can connect many molecules together and check on quantum computer what kinds of properties it will have this connection of many molecules? It is because probably I think that this is hard part of at quantum mechanics level.
No, yeah, you can. I mean, in principle, those things are. I don't think we have quantum computers that are mature enough to do this, but there are kind of preliminary studies on reactivity, and then you have to kind of survey your potential energy surface. So basically, you are having kind of molecular fragments interacting, or different molecules that go through a reaction path that then at the end of it, you have like new molecules, formation of a new molecule or rearrangement or something like that. So yeah, that is possible, and that by itself is not necessarily too far or too in the fundamental level is not too different from what I'm talking about here. It's more that increases the computational demand, but the fundamental theory and algorithms remain mostly the same.
Okay, thank you. Sorry for sorry.
Yeah.
You can continue. Thank you very much.
Yeah. Oh, great. Thank you for your question. Yeah. So in the previous slide, I think I mentioned this word gates, and in terms of quantum computers, they are not, in a very general sense, they are just what we call unitary operations. And for something that's relatively obvious, so a qubit being a two-level system, it's not a natural choice to represent operations and states in qubit space as and associate that with spins. So that's why spins are very pervasive in how we deal with quantum computers. So this is and then here the Hamiltonian here is what we call the electronic Hamiltonian, and how we would be generically represented as a sum of tensor of Pauli matrices. Now, part of the reason why this is so challenging is in our case, the electronic Hamiltonian, it grows as n to the fourth power, n being the number of basis functions. So and then once you have this mapping onto qubit operator, so we have lots and lots of those, what we call like Pauli strings. So each of them need to be each of those have their own statistics. So we need to prepare a state, observe each one of them many times to get a good sense of the distribution on their eigenstates. But we are not interested in the eigenstates of these Pauli words, but rather in the eigenstates of age. So that's a very tedious process that we need to repeat many times. So that's part of the reason why this is so challenging. Or in other words, there is a very large measurement overhead associated with like a straightforward / naive way of trying to estimate eigenstates of the electronic Hamiltonian. So this is a simple, like a very quick overview that underlies a lot of what I'm talking about here. So we start from what I call the molecular Hamiltonian. We consider electrons and their positions and their kinetic energies, and their positions in terms of electrostatic interaction. Same for the nuclei, which we assume are moving point charges. And then we have also electrostatics between electron and nuclei. So we make this a bit easier by imposing this Born-Oppenheimer approximation. We say the electron move much faster than the nuclei because they are much lighter. So if we can assume that at any point in time, from the perspective of the electrons, the nuclei are fixed. So we decouple the wave function, which would otherwise be dependent on both nuclear and electronic coordinates, to be parametric in the nuclear, the position of the nuclei. So then we start by solving mean field system of equations, which we use Hartree-Fock most of the time to find the determinant, or the one particle solutions that minimize the energy. And then we rebuild, we can think of that way, like we rebuild what we would be a many-body wave function by considering excitations out of this mean field solution, as I show here. And then turns out that if you add all the possible excitations that your basis set can comport, then you basically reach the ground state within the one particle basis approximation.
Can I have a question also for this?
Yeah, please.
Sorry. Because at this level, when you use a creator operator, you are still on the quantum mechanics level or not?
Yes.
Why? Because in my opinion, it is not a quantum mechanics, it's quantum field theory level, because you have an operator of fields of operators, yes? So this is not Hilbert's typical two-dimensional Hilbert space, but you have Fock space when you have just one vector and you can create other operator. So this is something mathematically this is near the same, but not the same. Could you say something about this?
No, I see your point, and I honestly am not equipped to discuss quantum field theory. That's not something but I understand the distinction, and I agree with you. Yeah, this is Fock space. This would be Fock space, yes. And I understand the distinction. I mean, I appreciate the distinction. I don't know if I can comment on or yes, I know this. You can see this second quantized algebra from the lens of QFT, but again, I'm not equipped to delve into anything more than that.
Okay, because I can ask about so how you understand, for example, entanglement here, because it's not, you cannot construct a tensor product of your space.
Yes.
Okay, but this is just technically. So
yeah.
if you know what is difference, you can go further. Thanks.
Yeah. Now this has very practical consequences. Because the fact that you can't write your many-body wave functions like a tensored form, which follows from like Fermi statistics, then makes it is yet another reason why this is so hard a problem to solve. Yeah. So the last bit here is that we call the grounds. One of the methods to reach the ground state, if you have a linear combination of all these, the contribution of all these excitations, then you basically do what we call full configuration interaction, and that gives you your ground state. So this is a kind of a little cartoon to represent the variational quantum eigensolver, which will be kind of underlying some of the results that I'm going to discuss later. So basically you have a classical preparation stage that you basically encode. Once you define your problem, then you have some sort of encoding that takes you from whatever way you represent your problem into something that the quantum computer can understand and handle. And you prepare a state. I'm going to talk about this part a little bit later, that we have like a predefined form that called an ansatz. Then once you prepare the state, you perform measurements, you observe your state. Your quantum state preparation depends on parameters. There are classical parameters that we map onto rotation angles. And this is embedded in some sort of a classical optimization routine, and you have this feedback loop until your optimization routine determines that you have reached some sort of minimum, usually a local minimum, and that kind of spits out your result. Okay, so now we are in position to actually just start talking about what we came up with and what is novel about this. So yeah, we work within this framework of a couple cluster theory. So the basic idea. So if we recall a couple of slides ago, I talked about the full configuration interaction. So I use this gamma or this omega as a generic operator that basically maps your mean field solution onto your target state. And it will do so through this through some form of this operator T, which is some sort of collective effect of all the chosen excitations. Now, one requirement that we have is that the wave function must be what we call size consistent, which means if you have two non-interacting system A and B, the energy of the whole system should be the sum of the energies, and your wave function has to be separable along the lines of the two systems. So that hints at the right form of this omega operator being an exponential of the excitation operators, which is the hallmark of the coupled cluster theory ansatz. So T, like I said, we can define how many of these excitation operators we want to include. And this is a general form for them. So obviously, the more of those we include, the harder the problem becomes, but then you also increase the accuracy. You can, with that in mind, we can go back to our good old Schrodinger equation. Here I'm talking about the time-independent and non-relativistic version of the Schrodinger equation. It then within this framework, it would look like this, and we can do a little bit of math here, and if we multiply by e to the minus t, we can invoke the Baker-Campbell-Hausdorff expansion. And then it naturally truncates with this fourfold commutator, which is nice. I mean, oftentimes this never terminates. And then we determine t. So the t has, parameters to be determined. If I go back here, you see the little t's down the bottom here. You have to find those values in order to minimize what we call residual equations, meaning minimizing those projections onto spaces that are orthogonal to the space of your mean field that your mean field solution lives. Now the drawback is, okay, so like I said, it naturally truncates with a fourfold commutator, but t is not Hermitian, so that means e to the minus t is not is not e to the t dagger. And then it also has, so another consequence is it's not variational, and then you don't have this dual relationship here. So in fact, in coupled cluster theory, you have basically to solve your problem twice, because you have to find right hand solutions and left-hand solutions. But why was it called? Yeah,
sorry. So what will be with because in quantum field theory or quantum mechanics you use unitary operators because you want get information that probability is conserved. In this type, you don't conserve a probability of changing the states. So what is the proposition, how it should, this is something like that your solution will be defined from one coordinate system, and for other it could be changed.
'You're right. Now we don't we don't, on one hand, yeah, you preserve the eigenspectrum, you can see, because e to the minus t times e to the t is 1. But yeah, you change the wave function, you change the metric of the wave function. So you're basically solving for a different you're solving for a different set of states that happen to have the same eigenspectrum. But yes, you're right. So it maps onto a different state. It's not the same, maybe to a different space. It's a different. You're talking different solutions here, different functions.
Okay, thanks.
Mm-hmm. So, yeah, I mentioned this bit of information here before. The cost of computing the exact answer in a basis of what I call like Slater determinants would be it would scale factorially. So it's obviously not something that can be applied to extended systems or large molecules. So one idea is that we restrict this method to only what I call like low rank excitation manifolds, meaning, single double excitations or single double triple excitations, and even triple excitations tend to be very costly. You can see the associated scalings here. Yeah, for people who are familiar with, say, density functional theory, if you like, say, like local density approximation, it scales as n to the third power. So not even simple, like the simplest level, which is singles and doubles in couple cluster theory, is n to the sixth. So that gives you a hint of how demanding this is. And it turns out that this approximation is fairly good, not quantitative, like it doesn't give you, say, energy levels that are that can be directly compared with experiment, for example. But it oftentimes provides good like qualitative features, and it's not even the quantitatively speaking, is not very far from experimental results. And the nice thing about this theory, it can be systematically improved. So if you singles and doubles is not enough, so you can always go up in the ladder, and eventually you get there. So the whole argument behind what we call this method gold standard, CCSD, what we call CCSD parenthesis T, is we get the bulk of the energy through CCSD, and the effects of triple excitations come from perturbation theory, so that you get the bulk of those effects without paying the full price. So it's a very appealing compromise, which works quite well in a lot of cases. But remember that quantum computers, we apply gates in order to, impart information into a quantum state, and those gates are unitary. That's how the quantum computer works. I mean, there are ways to do non-unitary operations, but that's a topic for another day. So the point here is the standard couple cluster formulation is not unitary because of what I said before. So T dagger is not minus T. Now you can kind of engineer this operator tau here. That's how we define it. And this turns out to be unitary. Now, if we go back to and think of how we solved the standard couple cluster equations, and I said, well, there is a natural termination of the BC8 expansion. Now we are in that situation where it does not ever terminate. So we have an infinite number of terms. On the other hand, well, if we think purely from the e to the tau part, and not necessarily think in terms of implementing individual terms, the the hope here comes from the fact that this is the bread and butter of quantum computers. So this is what they are good for, to implement unitary operations. So that's why a lot of quantum computing and chemistry together are often discussed in terms of unitary coupled cluster and the variational quantum eigensolver.
Can I have a question for this?
Yes, please.
Is this theory connected something with PT quantum mechanics? Is also quantum mechanics without unitary matrices, but they introduce some kinds of symmetric operators like T and P. So you can treat this your system as an open system, and you can say, okay, my system is open, so I neglect the environment, and this is the reason why my operators are not unitary. Yes, so this is this theory by Carl Bender. Probably his work is connected with this PT symmetric quantum mechanics. This is one thing, and the second thing is if you use electrons as your qubits, as an excitation of the electron fields, do you try put second kinds of electrons like something like positron in Dirac solution, that you should use not one qubit but two at once? It is something connected with this or not?
Yeah, well, thanks for the question. So the first your first comment on open quantum systems. Yeah, so that's how you can invoke some of that to implement non-unitary operations, which is not what we are doing here. Now, if you wanted to try to implement something that is, similar to the standard coupled cluster formulation, which is not unitary, like you pointed out before, so that would be something that then would require something that, well, one way is thinking of your system as an open quantum system. The other one would be you have a system. Your system is, so then by an open quantum system, you can say, well, my system is in a bath. So the entire universe, so to speak, of your system and the bath are, they are still abiding by unitary operations, but then when you look at the math and your kind of impurity or your subsystem individually, they don't evolve unitarily. And the second question, and that's a good point, because I never thought about, or I never like put a lot of thought into it. I years ago I thought about how we could redesign these algorithms for spinors or something that, the Dirac equation, and there are people who think about how you can rewrite your common, like, typical second quantized operators here as like Majorana fermions, and there are apparently benefits to that, but those are all things that I haven't really tried myself, so I don't really have a good sense of, I can't really give a sense of how they would perform and how they would apply here.
Thank you very much for your answer.
And so basically connecting to the previous slide, again, so if we constrain ourselves to single and double excitations, this is somewhat ubiquitous in those applications of chemistry and quantum computing, but can we go beyond just this first level of approximation? And inspired by the CSC parentheses T, the gold standard of quantum chemistry, bring into the what we are doing some effect of the missing triple excitations within the unitary coupled cluster framework now. So these are the equations. I don't want to kind of spend a lot of time here, but just give a brief overview of what we did. Now, the fact that we are dealing with a unitary theory we are no longer having that issue that the bra is not the dual of the cat and vice versa. And so the theory is variational in Hermitian. And so what happens is the energy is simply the expectation value of the Hamiltonian. If we invoke the BCH expansion here, again, it doesn't terminate. But this is our starting point, and then we can resolve the tau operator in terms of its components, your simple T1s, like T2s, and whatever. So the typical excitation operators that I discussed before. And the basic idea here is like once you plug the definition of taus into your BCH expansion, it becomes like a monstrosity, but then you have to analyze the equation and start collecting terms through orders in perturbation theory. And so if you go up to fourth order in perturbation theory, these are the surviving terms. And now we can invoke what we call the residual equations, which in unitary couple cluster theory, it's very straightforward because they are simply the derivative of the energy with respect to your excitation operators. Now we see that so if we consider the equations for triple excitations, we see that they're quite simple down at the bottom here. And but then you can see that they also contribute in the residual equations for double excitations. So the idea is we use the result here down at the bottom, and then we plug that into the residual equations for T2. Yeah, so this is basically summarizing what I just said. We can simplify the equations, the energy functional equation by imposing the conditions that we arrived at by studying the residual equations. Then the lowest order T3 correction comes from solving the T3 equations here, and then we plug that into the T2 equations, and we land on this expression here down at the bottom, which is our energy, like the first contribution to the energy that comes from approximating triple excitations through perturbation theory. So if anyone in the room has ever come across many-body perturbation theory diagrams, this is what it would look like in that representation. So yeah, so moving on, and so now we have a way that tells us how we can basically understand and analyze the underlying unitary couple cluster equations to find out what pieces we need to start approximating elements that are missing in a given level of approximation. So we start with this UCCSD ansatz, and that gives you basically two options, because you can have a straightforward what we call full or standard UCCSD ansatz, which I say here is uniquely defined because the sum here is independent of the order. But then I'm not sure how we would even decompose this into, say, 1 and 2 qubit gates. We can simplify this, which has which is exact in the limit of infinite kind of replicas of the exponential. So you're basically like it is akin to those product formulas like Trotter and Trotter-Lee, Suzuki, but then the point here is once you make this sort of approximation here to a finite number of copies, so to speak, then well, first, it's not the same wave function anymore, and then the order in which you apply the gates that derive from the excitation operators becomes very important. So you need to specify the order into which you want to write this ansatz. So we tried both, and then we predetermined this order here, where we apply gates from double excitation operators first onto the mean field solution, and then single excitation operators later. And then we subject this to the typical VQE algorithm to find the optimal values for our T1 and T2 amplitudes. Okay, so these are the results, and we need to kind of look into the one that's like the gold bar and the bright green bar, and we can see that there is no clear how can I say better choice between the two, but I'll say they are pretty robust. We can see that the errors, because the error here is signed, and even though unitary couple cluster theory is variational, by virtue of adding that perturbation correction, it will break the bound, so it can overshoot and then you can have an energy that is lower than the ground state energy. But even then, even when you do that, even though you're like overshooting, your error, in absolute terms, tend to be much smaller than if you did not add that correction, and it often rivals with other ways of adding triple excitations. So this is like a collection of handful of simple molecules. Something that's quite common in quantum chemistry is like one way that we can kind of try to break the methods and push it to the limit is study how it behaves when we start pulling a molecule apart. So N2 is a textbook example of how make it, how inadequacies in your theoretical treatment will appear, because this is N2 has a triple bond. So then once you start pulling apart, you have like a six-fold degeneracy in the orbitals, and then that becomes really hard to treat if your method is not very good. And we can see that we know methods that are very dependent on perturbation theory, like CCSD parenthesis T, and even the normal formulation of couple cluster CCSD. They start off well. They track the solid lines that are they follow the qualitative profile of bond breaking, but then eventually they start deviating because the perturbation theory formalism, it depends on the denominator of orbital energies, and once they start becoming degenerate, and actually if you go further and start pulling this molecule more and more away from each other, the atoms more and more away from each other, you will go to minus infinity. But you can see that even though there is some error down in the bottom here, it's quite small, and it's tracking the qualitative profile really well. So that shows that this idea is very adequate and very theoretically sound. So in conclusion, so we basically introduced this idea of using perturbation theory to account for missing terms in the UCC formalism. Now, what was kind of a surprise is, even though the gold standard is this UCCSD parenthesis T, which is, you have a slew of different terms that compose those perturbation theory derived approximation. The terms that be the analog of the UCCSD parenthesis T don't show up in the unitary couple cluster, but only one of them, which is what we call square bracket C. So all these corrections are purely classical. So once we find optimal values for our amplitudes through VQE. So that extra mileage that we get from the perturbation theory correction is purely classical, so it doesn't require more quantum calculations, so we can get more accuracy and efficiency without necessarily more circuits or quantum computer time. And then here at the bottom is the reference that we discussed this in a lot more. So I think it's a good place for me to stop and then take a question if people have one or anything that I discussed so far.
If I can, I have 3 questions. Maybe
Yeah, go ahead.
maybe 2 remarks and 1 question exactly. Because at the beginning, thank you for your very interesting talk. It's very nice that you try to go to this quantum field theory level. And as I understand, you try use perturbative theory because you use just quantum electrodynamic level. Very nice. Maybe it's not so pure correctly theoretically, but I love that people try do something on other level than just traditional quantum mechanics. This is very great. So my question is that do you try formulate this this model on the something called Feynman path integral, or do you try derived some in quantum physics we called it Feynman diagrams? It is possible to derive something like that on your theory. And the third question is that as I understand, if you put more complicated molecule, it will be worst. Okay. Yes, probably. So do you expect some, where is the level of what kinds of molecule you can describe exactly or simulate exactly? What is the level of how many electrons you can put on your computation? Thank you very much.
Yeah, well, thanks, Sebastian. Yeah, the first point about Feynman path integrals. Yeah, I was even discussing with some colleagues this week because I don't know too much about it. The thing that I know, you have to formulate your problem through action, right? And
Yeah, exactly.
I mean, some people, I mean, there are people who study chemistry through path integrals, and it's not the kind of the most natural way. I think it would be probably better if you're doing, say, like reaction dynamics or something that is explicitly time dependent. And but I haven't come across like a case where I would need it. I think it would be interesting, definitely, to think about it more, but I haven't done any work on that. So the second part, you were talking about Feynman diagrams. I will say the diagrams that perturbation theory diagrams or a couple cluster theory diagrams that I showed before, they are somewhat reminiscent of the Feynman diagrams. They're different, but obviously we're not talking about QED here or scattering or anything, but I would say they take inspiration from those diagrams. And but now if you study, say, a molecule or something that is subject to some phenomenon where you need to study, where you like the proper way to account for something is by including QED, and some people do that, like very few, but some people do. Then you might run into a situation where you would start drawing like Feynman diagrams for molecules. I don't know. I've never seen it, but that's plausible. And then the third question, yeah. So I don't have a good sense, or if you can. The problem with a lot of these kind of more NISQ algorithms is that, and there's a criticism that is very valid, is that they don't have formal guarantees or bounds. So you don't know exactly how far you are from the ground state before you actually run the simulation. And that's assuming that you can actually find the exact ground state energy in order to compare. So if we run a very large molecule for which even a very large HPC cannot do. So you get a say like a ground state energy, and you're stuck with it because you don't know how good that is. But if you do some benchmarking and compare with smaller systems and molecules, and then you get a sense for how far you are. That's very kind of heuristics, and we don't have a way to determine like how far, how that bound would scale. So yeah, and then that also reflects in the corrections that we're proposing here. So most of the time, this works really well if this is perturbation theory, right? So if your zeroth order approximation is good, and in chemistry that usually means if your mean field solution is the largest contribution to the many-body wave function. So as long as you have very large support in your mean field solution, then this tends to be a very good approximation.
Yeah, this is what I suspect from
Yeah.
this theory.
Yeah, perturbation theory is ruthless. It basically only works. I mean, on one hand, it's good. It's like it's exact, so to speak, if you go to infinite order, but doesn't mean that it will converge monotonically or it can be divergent or things like that. But at the same time, if your zeroth order like wave function is not good, then yeah, it's a lot of work.
Yeah, thank you very much. So
Mhm.
maybe some other questions, not only for me. Sorry for that.
Daniel, can I ask a question?
Yes, please.
This is more about the background that you brought up in some of the early ones. You mentioned Feynman's involvement, which I was hoping you would mention that because his 1982 paper certainly was instrumental in quantum computing. But there's, I think, a common misperception about who came up with the idea of what we now call qubits. And that was really Yuri Manin when he, in 1980, 2 years before that, he came up with this idea of virtual computers as an abstraction for molecular level computation, dealing with the same issues you're dealing with, which is the extraordinary computation costs of even simple molecules. So I'm just wondering if you, when I read Feynman's 1982 work, I don't see qubits. I see something more like an emulation mode. He seems to be talking about fighting fire with fire. You take the wave, as much of it as you can, and its properties, probability conservation being an example, and you use that to let it do the hard work for emulating some other system. So I was just wondering if you had any comments or if you're familiar with Yuri Manin's work. And like I say, it was an interesting little kind of a quirk in the history that I think Feynman's work is somewhat misconstrued, because he had it was definitely a different approach. The approach he proposed in 1982 is not the one that I see when I look at modern quantum computers, because he never got bits. He never mentioned bits. He never even he didn't touch that. That was Manin who did that 2 years earlier. So just any comments? I just was curious about the history. And of course, it could have some relevance in terms of the types of problems you're doing too. I don't know if anyone's ever really done Feynman's emulation approach.
Oh, that's a good point. Well, neither do I. I mean, I got bits and pieces from Manin's work. I know it's in Russian, so I admit I haven't read it. Like I don't know Russian, and I know there are translations out there.
Yeah.
But yeah, no, well, for those reasons, I'm much more familiar with Feynman's. And the thing is, like the 1982 paper is actually a transcript of a talk that he gave, which is kind of speaking more like, high level, off the cuff kind of thing. But I do agree with you. It's much more, say, a kind of a high level, say, which is, he doesn't go down to like components or what the computer would look like or anything like that. It was more like conceptually what you would want to get out of it and how you would operate, more of a kind of a black box sense than to just necessarily saying, well, these are how information is processed and how you actually build something. So to the extent that I can say, yeah, I agree with you. I mean, that we are very, what we actually do is not very close to what Feynman had in mind. If we can get something of a computer out of out of what Feynman was talking about at the time.
It's closer to Manin, but Manin didn't get into qubits either. But Manin did most definitely bring up the idea of abstract computers, of computer instantiations, a virtual universe of computers. So it kind of led the path into going to the bits. So fascinating little bit of history. Thanks.
Oh, thank you. Okay, so moving forward here. So this is another paper that we worked on after the paper that I discussed, which is the main idea here is, can we apply a similar reasoning, trim down that ansatz even further, because that ansatz is costly to implement on a quantum computer. So the bulk of the, what we call a correlation energy, which is which is some sort of a, how we would look at it, like entanglement through the lens of a chemist. But the basic idea is like in an mean-field solution, you have individual electrons kind of navigating through the mean field generated by the other electrons. Now, if you want to account for the actual interaction among electrons, then you have to go beyond mean field. And then once you do that, in the lingo of couple cluster theory, that's done through, or the first level, or where it first appears is when you introduce the double excitation operators. And then the single excitations account for what I call orbital relaxation, meaning how your one particle basis respond to now being in the presence of some sort of instantaneous interaction among electrons in a mean field. So, and then short of that limit of full configuration interaction, which is like the limit of, considering all possible electronic configurations, when I say the energy depends on the mean field solution, is that if you throw different mean field wave functions here, you get different energies. If you do that for full configuration interaction, then it doesn't matter. It all washes and you get the same energy. And I say it can be the effect of your mean field solution is fairly inconsequential if you add this term here, which naturally appears in couple cluster theory, and it is it has different names. I mean, some people call it Bruckner orbitals. It's in physics, I think it's known as the Thales theorem. Anyway, it basically kind of largely negates the effect of a mean field solution by performing this rotation of all possible single excitations. Now, if we just recap a little bit on the constitution of the ansatz, now we want nothing but only double excitations. So it simplifies the problem, quite a bit. And we can do the same thing in unitary couple cluster land. We get this kind of UCC-D ansatz here. And you can go a step further and consider only the diagonal terms of this double excitation tensor, which later I'm going to comment on. This is not a very good approximation, but it's a possibility, and we have some work in the pipeline that appears to be working really well with this, but that's not something I'm going to talk about here. So yeah, this is just a summary slide of what we did, similar in spirit to the discussion that we had before. So yeah, can we, the motivation here, can we use similar reasoning within unitary couple cluster to correct for, missing single excitations? So we, again, invoke that fourth order energy functional. Here I recall Now the T1 residual equations, so the residual equations for the single excitation equations. And we can see that, and it happens that if you analyze these equations from a perturbation theory standpoint, you see that the first place where T1 appears is in second order in perturbation theory. So there's like some math here, how we rearrange the terms, and we end up with, now basically by paying more or less the same price, because all that we are doing is we solve the equations for T2, and now how much can we afford in terms of single excitation effects from that T2s that we solved. So we see right off the bat that we have a term that shows up in second order, but we can also have a term that shows up in third order. And then once we use the second and third order correction to the amplitudes, we realize that we get two terms, one that contributes to the energy in fourth order in perturbation theory, and then another two terms that go up to fifth and sixth order in perturbation theory. So these are the corresponding diagrams. So basically you have second order and the third order, and then you kind of can mix and match them in different ways. So that's why you have fourth, fifth, and sixth order contributions. So this is basically the same slide that I showed before, but now removing contribution from the single excitation operators. Like I said, we subject this ansatz to a variational quantum eigensolver in order to determine our tau2s, from which we extract C2s that we drop into the energy correction equations that I showed before. So we looked at a similar set of molecules here. You can see that the corrections that we derive also perform really well. Now the target here would probably be would be CCSD, because CCSD would account for the entire effect of single excitations. But perturbation theory works in mysterious ways sometimes, because you can see that often we get better results, meaning the error is smaller by not accounting for the full effects of singles, but only accounting for, singles partially. And we see that this the benefit is evident for all these. It's only four data points here. We have more data coming up, but yeah. So just judging by 4 molecules in their equilibrium geometries, we can see that we get more mileage by doing this approach that we are advocating here. Now, this is actually much more drastic when we start stretching those geometries. You can see that the error, the scale here is dominated by couple cluster with only doubles and couple cluster with singles and doubles. But even then, if we analyze the other molecules, the molecules that are not impure, and then you have 2 variants of water, one when we pull only a single hydrogen oxygen bond, and then the other one where we pull the 2 bonds symmetrically. We see that even on the other cases, the errors that we obtain by our approaches here, the 4S and 6S, are very much on par, or excuse me, better than what we would obtain by including all contributions that come from single excitations. In this paper, we studied a few more cases of different dissociation curves. We see that, perturbation theory, you get a very kind of fortuitous error cancellation, because the inclusion of only doubles is obviously not appropriate. See that if you look down at the bottom, you see that the error is the largest for the blue lines, which have to do with the complete exclusion of single excitation effects. But then, even if you add all the single excitations, there is a fairly large portion of this curve that is in which the errors are larger, for including all the effects of single excitations when compared to the pink and or magenta and red lines. You can see that errors are smaller, and in the sixth order correction, yields very small errors. Obviously, they come from perturbation theory, so eventually that denominator that I talked about catch up to you, and then the degeneracies start kicking in, and then you start going to minus infinity. But as far as the region that is close to the equilibrium where the molecule lives most of the time, this is a very good approximation. This is a kind of a toy problem, a model system that is fairly challenging. So you have a chain of 8 hydrogen atoms and you start pulling them apart symmetrically. We knew ahead of time that this would not work well for CCD or CCSD. But it shows that in part you can prevent or mitigate this effect, at least for some time, by not adding all the contributions from single excitations. As we can see, the plots here show that the errors are much smaller for the different flavors of unitary couple cluster theory here. And again, the errors that we got from doing partial addition of single excitation contributions seem to be most satisfactory. And we looked into the effect of different particle bases here. So SCO6G is a small, what we call minimal basis. The one down there is the next step up in size. We see that qualitatively most of the conclusions remain the same, but we get much larger errors for when you don't include single excitation. See, the blue line here is much further from the other lines than you would otherwise see in the picture where you have a smaller one particle basis. But the other lines that include different levels of single excitation contributions coming from perturbation theory and even infinite order effects, we see that they are kind of similar, but now there is I think the effect of having a larger one particle basis makes the whatever is missing from the higher order terms more apparent here. Now that we see that there is a little bit more error coming from terms that are missing up to terms that probably come from orders higher than 6 in perturbation theory, as the error in the magenta and red curve are now larger for a large portion of the curves here. So in conclusion, we can, in various situations, recover very large amounts of correlation energy deriving from single excitations through our perturbative approach here. We found 2 main corrections that we can afford easily at the same price here, and to the 5th. Just a reminder that those corrections are purely classical, so we don't perform any more calculations or simulations. This is what I mentioned when I say PCCD, is that when we only include pair excitations, we constrain double excitations to diagonal piece of that tensor, and they are not, without further work, they are not quantitative. And I don't show them here because they would completely dominate the error scale and we wouldn't see anything else. So again, this is the paper here. If anyone wants to check it out. And so just a like a general conclusion for everything that I talked about. Yeah, so there is still a lot of work to be done in order to consolidate chemistry as like, well, the quantum computing killer app or whatever you want to call it, like to chemistry to be the end all be all application. But in one of the many efforts that we are seeing in order to get closer and closer to this reality, let's say this is a good one, and it is it can be mix and match with other strategies. It comes from perturbation theory, which is a very pervasive approach, and it can, I'm saying here, we get this extra mileage by using formalism that we are very familiar with and know more. By doing that, it does not incur more quantum computing time or more cost. And my student Zach Wyndham and I are working on various other ideas that are follow-ups to the work that I showed here, and ideas that we inspired by some of the things that we came across while we were doing this sort of work here. So yeah, I want to thank him. Zach's been a tremendous student and he's very smart, and a lot of this is stuff that he came up with. I want to thank DOE, specifically Basic Energy Sciences, for funding this work for a while now. And well, thank you all for your attention, and I'm happy to continue the conversation. Yes, this.
Okay, if I talk?
Yes, I'm done.
I was curious how you came up with this idea and why no one has done it before. You seem to be getting some great benefits. Is it just people didn't think of applying it? It seems like an interesting crossover. I was wondering what was your inspiration process on this?
Yeah, so when Zach approached me and said, "Oh, I want to work on this," I was like, "Well, I think it's a good idea. Well, why haven't why hasn't anyone done that yet?" I had the same question, and we were working on it, and I say primarily because I try to only kind of show the highlights here, but the math is very tedious. It's like pages and pages of equation, because once you expand like the energy, like the expectation value in terms of the PCH expansion, it is like hundreds of terms that you have to keep track of and say, well, this is this order in perturbation theory and so forth, and then you have to find all the constellations. So he did all of that. So he was very meticulous. And I think a lot of people might have gotten discouraged once they saw how ugly those equations were. And they said, wow, there's probably nothing here that's not worth it. So yeah, I can't really say for other people, which is the fun thing. What's kind of funny is that when we submitted the paper, one of the reviewers, after seeing our derivation, said, well, no, I think you should do this, this, and that. But then, well, it's easy for you to say after we have derived all these equations, because the reviewer behaved as though, they know what they were talking about. And I mean, they probably did, but the point is, it was not that easy to come up with this, because it's again, very, very tedious, very, you have to be very meticulous about studying these equations. That's my best guess, really, how nobody's done it before.
So Sebastian was the initial inspiration for taking the perturbation route?
Oh, what? I'm sorry, Terry, what's the question?
Sebastian was the original inspiration for taking the perturbation path?
No. I mean, Did I say something like that? They came across like that?
Oh, I misinterpreted something you said. You may have been talking about Sebastian's question during the talk. Or
No, no,
the-
that's not a
the initial
that's not.
idea, the initial idea came from who?
Oh no, the initial idea came from my student Zach.
Oh, okay, I'm
Yeah.
sorry. Okay,
Yeah,
sorry.
so that's my student here. Yeah.
I can be your student
Yeah.
I hate to admit that I
in the next life.
Sebastian and Zach together. Sorry, that was a complete
Yeah. Maybe I
One of
stumble on my words and did it. Okay.
That's fascinating. Fascinating. The intimidation factor probably was the biggest reason why nobody tried it. It was just a lot of work to do it. So
Yeah, I agree. I mean, I think I would probably not have done it myself if not for Zach being like so determined. So no, I'm gonna do it. And yeah.
Okay, we have a question from Jordan. Jordan, if you can unmute yourself and please ask. There will be a question from Jordan Janon or not?
Hello, can you hear me now?
Yes, we can hear
Oh.
you.
Okay. Daniel, hello again. Thank you for coming to see us. Good to see you. My
Appreciate
question is interesting that what you were saying. I just read something recently, and a disclosure here is this isn't my area. I'm a technologist, but what you said, there's a recent paper that it's a simulation of molecular dynamics, and they were kind of preaching the same thing about the Newtonian simulations. And their thing is this large-scale atomic molecular massively parallel simulator, LAMPS. And it's basically stating that the computation, it's not there yet, basically. It's not ready for prime time, the quantum computing for quantum chemistry. And these simulators, they're using these, parallel, clusters, and that's the norm. And this really is your area of expertise. Do you see more people using where we are right now with quantum computers and their capabilities? Are more and more people integrating this into the workflow for the simulation, for actual research? How are they implementing this right now?
Well, that's the million-dollar question right now, because I think we are pretty close to, well, we are definitely in a lot of fields, not just chemistry. Let's say, obviously, I'm talking about stuff that I don't know, but like I have colleagues here at the lab that are, CFD experts, and then, even like climate modeling. We are very kind of constrained by what we can do. Even, well, RNL is famous for hosting the, fastest supercomputers in the world for, decades now. And we are always constrained by what we can do. And at the same time, if you look at some of recent papers from IBM, they are doing simulations that just the kind of processing of the data require high performance computing facilities. So that integration is natural, and then I would say the past like year or so that people started taking seriously and started working on it rather than just kind of just postulating or philosophizing about it. So yeah, I definitely think this is the future. We're going to see a lot more of this in the near future.
Thank you. And then my other question is, what's been going on with your other work with the XA? I forgot yeah.
Yeah.
Has there been
Yeah.
progress, work on that? What's been going on that side of things?
Oh yeah, I mean, I was debating whether or not I was going to put like Elisa's slide here in this talk, and I decided not to. Maybe I should have. But yeah, thanks for bringing this up. Yeah, we are working on it. We are we have some work on compilation and more, which kind of touches on HPC integration as well. I am leading a project on that. That is the integration is the main concern. So yeah, we have. I would say we are not. I mean, a lot of the stuff that we are doing with XACC is in support of other things and other projects that we are working on. So a lot of the new features come from it's like they are derived from all these other projects, but it's being the development is still current and ongoing. Thanks for asking, Jordan.
Thank you. That's good news. I'm really interested in that project. So thank you for the update.
Thank you.
Just wonder about the theory seems quite complicated. I just wonder, how would you validate your theory?
Well, you mean validate the
All this work with experimental work.
Yeah, you have to. Well, there's like two levels really. There is a level which what I'm doing here, where we compare, we assume that we fix a reference and say, well, since we are approximating the effects of single excitation, so we say we're going to compare against inclusion of infinite order single excitation, so all the effects of single excitations. The second level, which is something that's we are not quite there yet, by we I mean the community, is like to be able to immediately compare with the experiment, which is the ultimate goal. I mean, if your computation is correct, it should be comparable with the experiment. And that is something, but again, in both cases, you need to, in situations like this, where, like I said, we don't have formal bounds or guarantees, so we never know how far we are from a specific value until you go ahead and do it. So yeah, there is no other way to validate this other than run a calculation and then see what you get. Now you do a lot of benchmark, and then eventually you get a sense of, say, well, we are usually this far from reference X or experiment when that's possible. Does that answer your question?
That's fine. Yeah, thank you.
Okay, thank you.
There's some written questions on the chat earlier.
Okay. You wanna read the questions, or do I go through the chat and ask them?
Oh, sure. The first one is from Jervis. He said, can you explain what you mean by preparing a quantum state via a time order sequence of gate operation?
Oh, yes. So the idea is, so you have gates. I mean, the same goes for your conventional computer. You have what they are is not that important. What we should keep here is the concept, which is like you start from a state with your machine has some information, and then you want to manipulate that state such that it will in the case of a quantum state, your state will rotate such that now it display different information. So by saying that circuits are the time ordered sequence of gate operations, that means you have the order into which you apply the gates matter. So there are, and then in order to reach a desired state, you have to apply those gates in a specific order. That's what I mean by that. Is I don't know if by saying time ordered is somewhat confusing because at that point we don't have necessarily a concept of time or time as in seconds or milliseconds or something of that sort. But what I meant is you apply gate 1 and gate 2 and gate 3 and so forth, gives you a state, and if you apply gate 2 and then gate 1, that can potentially lead you to a different state. And there are protocols to prepare certain states. So that's what I meant.
If I can,
clarifies.
the time ordering is maybe some we can call mechanism used in quantum field theory in natural way. So this is the reason why he used something like that, probably.
Yeah, thanks, Sebastian. I think maybe there is a connection there if you want to be very very formal. But yeah, I meant something higher level. Thank you.
Okay, and the next question was, is omega operator always bijective or something else? Maybe someone who gave this question could say something more about what he mean by bijective operator, or which place he means.
Yeah, well, yeah, if the person who asked wants to clarify, I think I know what they're hinting at, and if I'm wrong, they can interject. But
Yes, I am. Hi, I'm German.
yes,
I am the one who asked the question about the omega. Yeah, it was just in the I think toward the beginning of your presentations.
Yeah.
After. Yeah, it's just a question came when you were giving your presentation, so you need to go back to the slide so that I can have the idea how I asked that question.
here, right?
Before, probably, where
Yeah, before, I think.
where you define omega operator.
Yeah, I think I first define it here, and then
No, you have here you have
Yes,
first definition.
yes, right here, you get it. Yeah, this is that. Yeah, my question came from reading this slide. When you say let omega be an operator that maps, I'm thinking about the map operations.
Oh, okay.
Of state 0 to state psi. So is it a map a bijective operations, or it's a different?
Maybe. Yeah, I think
is
I
it
was
a bijective map or a different map?
excuse me. I don't think it's bijective, but I use maybe I should be a little more careful with my terminology here. I don't think it's bijective. I think you would because bijective you would imply that if I apply omega to psi, I get 0 back, right?
Yeah, no. When I talk about bijective, it means like if this association, like for one state 0, for one state cutoff 0, we have only one state phi, one state cutoff phi. Is that what I mean?
Okay, yeah. No, in that sense, yes. Then it would be bijective. Now I don't know how we would. Well, the caveat here is it's probably in that sense, like one-to-one mapping, it's probably bijective. But because we determine omega by looking at the energy, if your state is degenerate, then I don't know how that would change. But then I'm kind of going on a tangent here. But to answer your question, I think it's bijective. I don't think you can map onto different states, or the operator itself would change if you start from like a different mean field solution.
Thank you. That was what I wanted to know. Thank you.
Okay, well, no, good question. I'm gonna look it up really because I think I should know this very well. I never thought about this. Good question.
Thank you.
Okay, and there is one question about technical issue that on page 18 should be something like T dagger is not equal T2 minus 1. But I don't know, I don't see who was asked about this.
Dr. David, you asked this question, asking the first one.
Yeah, I just confusing. So you have minus t, right? That's not inverse. Should that be inverse, right? The t tag not equal t inverse, not minus t.
Oh, yeah. Now, you're right. I think I went one step ahead, but yeah, in principle, yeah, you're right. Now it happens that the t. Yes, yeah, you're right. I was thinking, yeah, I kind of overlooked this because e to the t. So if I have the exponential e to the t, and then I, complex conjugate it, then the complex conjugation goes into t, and then e to the minus t is the same as the if it was Hermitian, it'd be or unitary would be.
Yeah, but minus why can come from minus? Why is minus t's come from? Minus t, I don't understand. Even next one here is say the t minus t tag is unitary. Why have minus? That should be operated like one by one consecutively instead of have a t minus. I don't remember what you have t minus t tag or something like that. Why is that kind of equation not operated like t t tag times t inverse? I don't know what you mean t minus. I mean t minus t tag. What's that mean?
Yeah, no, yeah, I understand it's confusing, but the condition here, t dagger different than minus t, is actually this is where you land when you look at it through the exponential of the operator. But I agree with you. The way that I put it here is confusing. I should have worked with the exponential. Yes, I mean, sorry about that confusion.
Should have t inverse, right? I think.
Yeah. But then it would come out e to the minus t, because that would be the inverse of e to the minus e to the t dagger. But then because I was playing with the t's and not e to the t's, that became a little confusing. I agree. I should, but I think. Thank you. Yeah.
Okay. Thanks.
Okay, do we have any
I have
more
one last question.
Yeah, you can.
Hello?
Mm-hmm.
Yeah, just start.
Yeah. Do you have some open source project that you want people to contribute, work on those?
Yeah, that's what I'm gonna put here in the chat. Let me.
Oh, cool.
Yeah, that's what Jordan was talking about. If you look it up, let me, because so you go to, yeah, I don't want to stop sharing here and look it up online, but yeah, it's called XACC, and that's the software framework that I use to where I implemented all this and that I use to run those simulations. Yeah. Yeah, thanks for the question.
You're welcome.
Okay, so probably we don't have any new questions, or we have?
Daniel, one quick one. For the XACC, I'm seeing a big push. Everybody's moving to Rust. They want to kind of get away from C++. Is that part of the workflow happening with the XCC as well?
Well, Jordan, that's a good question. I will say there is no plans in the near future to migrate to Rust. And I understand where you're coming from. There's like even security concerns. But yeah, for the time being, no, there hasn't been any discussions on changing XCCC. We haven't had a reason to do that yet. Maybe because we are not faced with the same concerns. But yeah, even IBM and who else that I saw the other day. Yeah, I mean, I think slowly there, with time we may do that, but there is no plan for the near future.
Gotcha. Thank you.
Thank you. Do we have any more questions? I think we're through the questions in the chat, I guess.
I have one question. What is the most important thing you found out as a result of this?
Oh, the most important thing, maybe to have some, like a student or somebody who's willing to do things that will scare most people away, because I was not gonna do it myself. And I think the fact that we managed to do it first, even though the fundamental theory here is known for, I don't know, 50 years or so, at least 30 years. And the fact that people haven't done it, I think it's a testament that this is kind of hard, or it's not straightforward or easy, at least.
So Daniel, question for you.
Yeah.
I assume all your simulation is based on XACC.
Yes.
Correct?
Mhm.
How easy we can implement in the use IBM Qiskit? Is it hard or easier, or
Well,
because I won't be able to teach it. I'm gonna training for NS training for the students, and we familiar with the Qiskit and also Pennyland. I'm not sure we have time to teach student another framework.
Yeah, David, that's a good question. Yeah, I mean, if you want something to teach students, I honestly will be honest with you. This is probably not the best tool, because this is
Okay.
a lot of the features are kind of performance driven, and we do that more for like research, which because of the pace at which we need to do things, we ended up like sacrificing a lot of like user friendliness.
Yeah, but talking more because I'm not for my school students. I'm actually we can have a summer school for the researchers. We don't want to have really useful. We don't want toys. We want to use for people actually use the quantum computing for drug discovery. So your paper I read it more carefully because I'm a computer scientist. I'm not chemist, so I want to read it more. So I make sure I understand the concept. Teaching the chemists so can use your tools, kind of not just for no toys for next 2 years. We want something useful. Actually, people use your tools to actually discover new materials. That's the goal, right?
Yeah, for sure. Yeah, before I think we started the talk, Helen asked me if I would be willing to share the slides. Yeah, and I am, and I told her that I was gonna add my email somewhere in the slides, so if people want to reach out. So David, you are more than welcome to, once you get the slides.
Yeah.
No,
I will find your LinkedIn, so I request
yeah.
LinkedIn.
Oh, yeah, that's great. Yeah, that works too. Yeah,
I will do that. Thanks.
Yeah, thank you.
I have a question. You hear me?
Yes, I can hear you.
Yeah, I'm sorry for asking my question. Yeah,
Okay.
when we in the case we apply a lot of gates on a set of bits, how many bit string can we expect to have?
Well, let me go. Oh, shoot. So if we go here, so this is no, this is
Yeah.
better. So
Yeah,
this
we
is
can take yes, we can take this example, yes.
yeah. So the second part here, the P dagger, Q dagger, SR. So that's the bottleneck here. That's what determines the size of the Hamiltonian. So that's why we say it scales roughly as the size of your one particle basis to the fourth. And then it also depends on how you map your fermionic modes into spin operators. If you have something like Jordan-Wigner, which is the easiest one, but it's not very efficient, I think that gives like an 8-fold increase. So however many terms you have here in your second quantized fermionic Hamiltonian, you end up with like 8 times more operators. Now, for the problems that I studied here, I don't have off the top of my head the number of Pauli strings that we end up with.
When we have an infinity, or it depends on the size of.
Oh no, it's never infinity. It can be a very large number though. I mean, it can be like 100,000 or something like that, but not infinity.
Oh, okay.
Well, part of the reason
And
why is
all of them, they are like the result is always probabilistic, right?
yeah.
Oh, cool. Thank you.
Mhm. Do you have any more questions? Thanks, David.
Well, if no one else has any questions, I'll throw this one in here. Slightly a little off topic, but I'm seeing people are using, theoretically, and then they're implementing this into a production model in research of taking quantum computing and quantum theory into where human factors and simulating, basically they're using this to model the unknowns, basically. So it's basically looking at the optimization as well as looking in the forecasting of behavior, actually human behavior, and they're putting this in there in the chain, so to say. And it's an interesting situation in terms of what's going on with chemistry and that whole side of things. It's pretty clear, in the news and what you see and being published about, all the big people in the space of, from IBM to, the pharmaceuticals to all these companies that are using it in like automotive, aerospace, all those applications. And you see progress of using this or wanting to use this and what have you. So in that area of what's going on, you're saying it's the future. People are moving forward with this. IBM is pushing, a lot of advances. Microsoft is saying they have a lot of advances in this. I think PNLL and Microsoft teamed up for a similar thing where they're implementing more research and I guess proving, right, its value in this space. What's the next step here? It's basically where we go at this point.
So, Jordan, can you be a little more specific in like if you're asking where we go from here in terms of like my research, or like you mean like kind of the community as a whole?
Well, both. First the community and then where you're going.
Oh, I mean that's a hard question in the sense that well, there is like the perceived direction from what people are doing. But then I mean, you seem to be very on top of the news. So if you see what people like Psyquantum are doing, which is not a lot because they are very secretive, and you never know. That's what I'm trying to say is that what we know from what other people are doing, but every now and then there is some sort of a breakthrough. Even what IBM did a few months ago with some folks in Japan with this HPC integration that I was hinting at. And since they published this, it wasn't like some sort of like gradual path. So they just a little bit like came out of nowhere with this idea, even though people have been thinking about it and talking about it, there wasn't signs that people were working on it very seriously. And then eventually they showed this study. I would say this is definitely like one of the frontiers right now. Well, error correction is at pretty much like the ultimate goal of a lot of what people are doing. Now, people are trying to come up with some sort of a computational advantage with the computers that we have today, but because they have no performance guarantees, we never know. Like this is still an unanswered question. Can we get any advantage by using NISQ or like the computers that we have now? And then we have to just try things and see if they work or not. But now, I mean, the past like year or so, you had Quantinuum, IBM, QEra, maybe more, a few more companies showing, demonstrations of small error correction codes, and it's only gonna grow from here. So, and that's also another application that needs a lot of HPCs because there is a lot of classical, like data movement and processing that you can't do on a laptop. What I'm doing, I just briefly I talked about the HPC integration, and Zach and I are working on other directions that grew out of this work here, which is also like involved pushing forward with perturbation theory within this chemistry and unitary couple cluster space.
So the projections of what's being put out there, we're going to have 5,000 qubits by 2028 and all of these things. We're still well below, I mean, what's really needed, logical qubits, and to actually have something extremely useful, so to say. It's even, 50,000 qubits. We're starting, not even getting close to really usefulness.
Yeah. And there is different companies have gone about it in different like ways. You have companies that are focused on qubit count a lot, and some are focusing on. It's like, well, there is a little bit of a trade-off because the amount of resources are finite. So you put time and energy on making better qubits or more qubits, right? So, and some people go about, well, their philosophy and business models are different. So some prefer more qubits and some prefer better qubits. Eventually we need more and better qubits, because that's the only way we can get to a lot of these applications that we've been discussing, that will, like, once and for all prove quantum computing is here to stay.
So for the naysayers out there, there's value even just doing this research because, like you said, things come out of it. There's quantum-inspired algorithms that improve the current system class. You know what I mean? There's a lot of value in this in all aspects of it. So I feel the people who are like, oh, that's not going to be in my lifetime, or there's no value in that. They all want to put their resources and money with generative AI. They feel that that's the solution for society or whatever they're thinking. It's like, I don't know.
Yeah, no, I agree with you. I mean, well, being a scientist, I'm driven by kind of more fundamental questions, and as in, like, well, you want to know why things are the way they are, and sometimes that's the beauty. I mean, in my opinion, I mean, and if it works, and in a sense of, like, from that you can come up with technologies of all the better. But just the fact that, like, we study things from this lens, like you said, of quantum algorithms, but also quantum inspired classical algorithms. I think that's in itself a good outcome of this. But obviously, I think it will be very pervasive as the technology catches up with all the like theoretical promises that we get out of quantum computing. Hey, Terry.
And by the way, Jordan, if you want to hear some interesting comments on generative AI, go to next week's session. I guarantee you we'll have a few. Daniel, kind of a broader question. One thing that always strikes me every time I go to one of these types of presentations is the exponentials and the massive level of computation that comes when you get just outside of 2 or 3 atoms. And yet our bodies are doing this quadrillions of times every second in every cell. Aren't we missing something about how to do this? It seems like we're somehow taking an unbelievably difficult way of doing something that there should be some way we can access that power that we know is there. And this is a Feynman-ish question, but it always strikes me. It just seems like we're doing so many explosions for things that the body does at almost zero cost and almost zero time. And there's got to be some way we can get hold of that a little more efficiently. Quantum computing is trying to, but then we seem to blow up in these explosions there. And in my personal opinion, I have some problems with qubits, by the way. I think more analogical quantum computing might be part of it. But any comments on why is this so hard when nature does it so easily?
Yeah, no, that's a good point. So in this kind of chemistry literature, where quantum algorithms for chemistry literature, you're gonna come across this term FEMOCO a lot, which is like an iron cofactor in like the enzyme that is central to nitrogen fixation.
Yes.
And yeah, so when we try to do that synthetically in industry, then we're still to this day doing this like 100-plus-year-old Haber-Bosch process, which is like very high temperature, very high pressure, very expensive / toxic catalyzer, like catalysts, and to get something of a decent yield. And then this enzyme in living beings, is like I said, room temperature, atmospheric pressure, no problem.
Just amazing.
Yeah, no, it's just amazing. Yeah, there's something. I mean, I cannot answer the question, but I share your kind of contemplation here, because I think part of the reason from a computational standpoint is the representation of the problem. Like when we try to go from a many-body wave function, break it down, now try to represent that wave function in terms of one particle wave function, that's a mean field approximation, and then build back up and try to represent like entanglement, like collective behavior in terms of individual pieces. I think that's part of the problem.
Okay.
That's more like some intuition.
Entanglement is fascinating because entanglement is based on the concept of non-local action. But then if you look very carefully at the examples of non-locality, non-locality is not quite what we think it is, because informationally it never happens until the information gets there. I forget his name at the moment. There's a famous physicist who was one of his, oh gosh, what is his name? But he made some comments about that, about how the paradoxes that we think are happening in entanglement, nothing ever changes at the remote site, was his point. Nothing changes. It only happens when you get that result. And I remember the first time I read that, and I hate that I'm not remembering his name at the moment, but it was so striking. I was going like, well, what does that mean? But he made a very strong point that all the speed of light, the constraints of the speed of light, special relativity, absolutely apply to quantum mechanics. And that means that there is no change. You don't change what happened to that guy's remote location. That's how we phrase it as entanglement, and that may actually complicate our computations, because we may be proposing something that's not hitting the mark quite right on how that goes. So there's some fascinating issues about the computational representation of entanglement. What does that really mean? And are we getting that quite right? I would argue probably we're not. We're too locked into a single frame, inertial frame viewpoint. And if you're not careful, that can just fragment the computation process, is at least a possibility of that. So I think some fascinating issues with that. Sorry.
Yeah, no, that's a good point. Yeah, at some point you start thinking about it becomes more philosophy than physics or math, which I think
it has to get to math, and that's the other thing is we deal with these with philosophical issues, but at some point this has got to turn into formalisms.
Yes.
I think we're missing some of the formalism. Yeah. For instance, how to represent non-locality. We do not have a good representation of non-locality, and I find that distressing, because if we don't, how are we going to get that really captured in an efficient way that is computationally better? The universe does it, so hopefully there's some way we can do it.
Yeah, I think that ties to what I was talking about, one particle representation, because when we think in chemistry here, we say, well, the Hilbert space grow exponentially because you have the fact that you build your configurations like in an occupation space, and then you have like your one particle wave function, your orbital can be either occupied or unoccupied, so it grows like to the end, right?
Right.
But if you think what like the tensor network people like to think is that you have only a tiny portion of your Hilbert space that actually is relevant, and then in there thinking you have low dimensionality entanglement entropy. So the goal is like, well, a lot of the idea is like a lot of the Hilbert space is dead wood, and it shouldn't be there. I mean, if you think about it, you should have a way to reason about the problem that you never have to like blindly search Hilbert space, because you're not gonna find the right answer if you don't know what you're looking for, basically.
By the way, the name of the physicist, oh, sorry.
No, go ahead. I'm done. Yeah.
The name of the physicist was Asher Perez. It was one of his last papers, I think the one on gravity, 2004, but Asher Perez. He had some very interesting comments that I found just baffling, which is why I loved it, because I couldn't contradict what he was saying. Special relativity is absolute. You cannot transmit information faster than the speed of light. And that means that non-locality doesn't work quite like we think it is. We reconstruct the path after all the information is available, and there has been some discussion about that. But the Hilbert spaces as a static representation of all the possibilities work fine. But what you're getting at is in any real situation, in a real model with real particles, it can't work that way. There's one of the slides I have, which I'll have next week, is, it gets infinitely dark as you go into infinite dimensions. And that means dynamically, kinetically, it doesn't make any sense. You can't transmit information from point A to point B in an infinite dimensional space. It fades out instantaneously, literally. We see that, in linear power on a linear one-dimensional space, 1 over r in a two-dimensional space, it just increases. So somehow the distinction between the static representation of Hilbert space and this more dynamic thing that you're hinting at is an intriguing area about how does it get constrained? How do we get this into a little more effective things? I think some intriguing problems there.
Yeah, for sure. Yeah, absolutely.
Daniel, I cannot refuse ask some question about the recent Nobel Prize. So do you have an idea, like the AI people get a Nobel Prize in physics and chemistry? Any comments? You don't have to say anything.
No, I mean, I don't have anything to say really. Yeah, I'm not competent to comment on AI in that, so I'd rather not.
Sorry, I put in the comment. It just kind of people weird like AI knows everything.
My talk next entirely about that, both the physics and the AI, and most of my career has been in AI. So if you want to hear some interesting comments about that, there is just a fascinating story with what happened at Nobel Prize. It was not anything what I expected when I dove into it. And I wanted to do a deep dive for 2 weeks into something that was extremely unexpected for me. So yeah, it's an interesting issue. And there very definitely some physics, some of the same kind of physics we're talking about here related. Because if you go back on Hopfield's earlier work, he did really good molecular quantum, it really was quantum computing issues that he was dealing with at the molecular level. And then he transitioned to the neural nets, to the artificial neural nets. So there's a fascinating set of issues on what happened with that. So for what it's worth, that would be topic next week.
Cool.
And with that, I gotta go.
All right.
Everybody.
Yeah, I think we have reached the top of the hour here. We're like 10 minutes past, really. But that's good conversation.
Yeah, would you mind to stay here? I see one more question from Chang.
Yeah, I mean, I can take it.
Sure. He asked why MBPT approximation outperforms UCC4.
Oh, yeah, I think it ties back to what I said about performance bounds, and that's even there. I was talking about performance bounds in sense of quantum algorithms, but it has validity here as well. I mean, I talked to my quantum Monte Carlo colleagues, and one of their criticism was of things like couple cluster or perturbation theory is that you never know what you're gonna get, and then once you get it, that's when you say, well, now you need to go one step up in order to make it better. And that being said, perturbation theory in particular, we rely a lot on what we call error cancellation. So because of what I'm showing here is energy differences, sometimes you can have an energy that is kind of bad, but then another energy that is bad by more or less the same amount. So then once you take the difference, they turn out to be good. So in chemistry, that's something that we rely on a lot. So yeah, that is a very fortunate kind of outcome of this study. But I don't know if there is some people have studied this, as in after you do like benchmarks and study this for a long time, get it's more of an intuition really, or a sense of why things should behave the way they do. I don't know if we can come up with some sort of like theoretical argument for why in some cases perturbation theory just works better than UCC. Yeah.
And a good feedback, great discussion. Thank you.
Yeah, no, I enjoyed it. Well, thank you for the invitation, Helen.
You're welcome.
Yeah, I will always have a good time with this group here. So, and yeah, I'll send you the slides, and feel free to email them. And yeah, and like I said, I told David, but that applies to everyone. People want to continue the conversation, want to reach out, yeah, LinkedIn works, and my email as well. Looking forward to it.
Sure. Thank you for all coming. Goodbye.
Yeah. Thank you. Bye. Bye, everyone.